Hello everyone, welcome to Cambridge Group. We are starting a new lecture series which is based on IGCSE Mathematics 0580 Extended Component. We will be covering each and every topic in detail. So without much delay, let us start with the very first unit, numbers. Before diving into the topic which is written in the unit 1, let us see what are the different topics that we are going to study in this unit. The first topic is the number system, in which we will be studying different types of number systems that exist throughout the history of mathematics. Then expressing a repeating decimal as a fraction, meaning the recurring decimal. Then we will study what do you mean by prime factors, HCF, LCM, and their applications, and also some basic arithmetic operations like addition, subtraction, division, and multiplication through the use of BIDMAS. Then we will study rules of indices and standard form, basically the exponent, laws of exponent. Then accuracy, in which we will be rounding certain numbers to the given significant figures or to certain decimal places, right? Then we will study directed numbers, basically the application of negative numbers. Then square and square roots, cube and cube roots. Then money and currency, basically the exchange of currency from one to other. We will be dealing this in this topic. Next is the time, in which some formula for average speed and distance, very old formula, very famous formula, distance is speed upon time, speed into time, and so on. We will be dealing with this, and also different types of representation of a time. Then we will be dealing with ratio and proportion, sets and Venn diagrams, percentage, in which we will be studying the concept of multipliers, and then simple and compound interest, and lastly the average speed. So without much delay, let us start with the very first topic, which is number systems. Now consider one scenario in which there is a class and certain students are sitting in this class. Now I need to count the number of students sitting in this class. So the natural thing comes to our mind is that I will start counting from 1. But when mathematics develop, I need to represent that count using certain symbols. Hence, the numbers 1, 2, 3 came into existence. So in order to count certain things, certain objects that exist in nature, we need certain symbols, and hence the system was of natural numbers. So natural numbers is a set of numbers which start from 1. So the numbers 1, 2, 3, 4 till infinite is regarded as the set of natural numbers, right? So the set of numbers, I'm writing that set of numbers in the bracket, 1, 2, 3, 4, 5, and so on till infinite. So this set of numbers is your natural number, which is start from 1. Now consider another scenario. Suppose I move out all these students. Let us say total number of students now in the class are 20 once you have learned natural numbers. So the count of the students in the class is 20, and I asked all the students to move out of the class. Now again I ask you that now tell me how many students are in the class. So the answer is obviously there is no one in the class. So now in order to represent this emptiness mathematically, we need another symbol. Hence the symbol came of 0. Although there are various applications of 0 or various motives behind inventing 0, but this is another motive as far as number system is concerned. So the next number system came was of whole numbers. So what are whole numbers? So if we add 0 to natural numbers, new system becomes the whole number system. Okay, the set of numbers 0, 1, 2 and so on till infinite, this set of numbers is called the whole numbers, right? So I can say that if I add 0 to natural numbers, that becomes whole numbers. All right. Now the third system came into existence was of integers. Sometimes these integers are also known as directed numbers. Directed numbers. Now idea behind inventing these directed numbers or integers, basically the negative numbers, right? So if I add negative sign to all the natural numbers, that becomes, including the positive natural numbers, that set becomes integers. So idea of behind inventing or discovering these negative numbers was to represent the direction. Meaning is, suppose this is my starting position and I'm moving towards right from my starting position, right? And there is another direction which is opposite to this direction. So if I'm moving towards right from the starting position, those distances as a convention are represented using positive numbers. And similarly, those distances which are towards left of my starting position, as a convention, they are represented using negative numbers, right? So in order to represent the sense of the direction, either forward or reverse, so we need another set of numbers or negative numbers, right? So the numbers from minus infinity till minus 3, minus 2, minus 1, so all these are negative natural numbers, we can say, plus 0 and then 1, 2, 3 and so on. So this set of numbers, as we know very well, these are integers, right? Hence the name is also given to them as directed numbers, because they are in fact representing certain directions, right? Similarly, the important concept or application of these integers or negative numbers is temperature. The freezing point of water is regarded as the reference value, and all the temperatures which are warmer or hotter than this freezing point of water, those will be represented using positive numbers, and the temperatures which are cooler than this freezing point of water, that will be represented using negative numbers. And freezing point of water is regarded as the origin or 0 degrees centigrade. Okay. Now next number system that came into existence was of rational numbers. Now what are rational numbers? There is a very, you can say, formal definition of the rational numbers, that any number which can be written in the form of p upon q, where q is not equal to 0, right? But that was not the idea behind inventing rational numbers, right? So idea behind inventing rational numbers was that if I say that there is a number which is 3 by 4, so basically it says there are 4 parts of a number 3, right? Similarly, if I'm writing 1 by 3, meaning is you are writing or dividing a certain thing into 3 equal parts. So what we are dealing with, we are basically dealing with the fractions. Okay. And the meaning of this can also be stated that 5 upon 2, two equal parts of 5, right? There are 5 things and we need to divide those 5 things into 2 equal parts. That's why it is written as 5 upon 2. Right? So All these numbers are called rational numbers, right? And they exist in nature also. Okay, so although there is a difference between fraction and rational numbers, so now we define a rational number as any numbers which can be written in the form of p upon q, where this denominator cannot be equal to 0. Now why this denominator cannot be equal to 0? It's a part of, you can say, higher mathematics, because uh, anything, any fraction which is having 0 in the denominator, that is not allowed. We say it is not defined, and sometimes we also say that it is infinite, but actually it is not infinite. It is either plus infinite or minus infinite. And once we go through the graphs of some functions, which will come later on in these lecture series, so when we will be dealing with functions and graph of functions, there we will see why the denominator cannot be 0 in any rational numbers. So for now, all the numbers which can be written in the form of p upon q, which also includes all those natural numbers, whole numbers, and integers also. Example, if I am writing an integer, let us say -4. So this -4 is basically -4 upon 1, and this can be represented in fact in the form of p upon q, and q is not equal to 0 in this number. So you can say that yes, this can be regarded as rational numbers. So I can say that all integers are rational numbers, but vice versa is not true, that all rational numbers are not integers, right? I cannot say 5 upon 2 is an integer, right? So as we are moving up from number system, the previous number system becomes the subset of the new number system, right? For example, if I say that nowadays Windows 11 is the new operating system, so that doesn't mean that it won't cover all the features of Windows 10, right? But yes, there are certain new versions in Windows 11, those can't be covered in Windows 10 or the previous versions of the operating system. So same case is with these number systems, that the rational numbers will accompany all those previous natural numbers that came into existence. Fine. And not last, we need to study the properties of these rational numbers also, the types of rational numbers, right? So you can write down types of rational numbers. Now there are two types of rational numbers. One is terminating, and second is non-terminating. Non-terminating but repeating. Sometimes we say recurring. Okay, repeating would suffice. Right. So what are terminating rational numbers? The thing is, if I find out the decimal equivalent of any rational number, if that decimal equivalent meaning if I divide a rational number with the denominator, if the numerator is divided by the denominator, that is the meaning of finding out a decimal equivalent. If that decimal equivalent terminates with a certain digit, then that rational number is called terminating rational numbers. For example, 1 by 2. So its decimal equivalent is 0.5. Here it ends. So we say this is a terminating decimal number or rational number. 1 by 4. Its decimal equivalent is 0.25. Terminating. Right? Similarly, you can say 2 by 5. This is 0.4. Terminating. And there can be more than one decimal places, but important thing is that the decimal equivalent must end with a certain digit. Means the number of digits after the decimal points are finite. You can also write this, that number of digits after the decimal are finite. Okay, so this is terminating rational number. Second is non-terminating but recurring or repeating. Example for this is very famous, which is of the type 1 by 3. Its decimal equivalent is 0.33333 and so on. So as you can see, there are infinite number of digits after the decimal point. And in short, all these repeating decimal are written as the digit which is repeating after certain decimal point with a bar. So here 3 was repeating after decimal point. So I will write this 3 with a bar or sometimes with a point above this 3. This is also another way of representing repeating and non-terminating. Right? Similarly 2 by 3, which is 0.66666. So all these numbers are rational numbers, but the category for these is non-terminating because number of digits are infinite, but they are repeating. There is certain pattern after certain digits. Okay, so this is the property of rational numbers. Now, next number system that came into existence is obviously irrational numbers. Because if something is rational, then obviously there must be something which is not rational or irrational. So what are irrational numbers? All those numbers, formally speaking, all those numbers which cannot be represented in the form of p upon q, where q is not equal to 0 obviously, then those numbers are called as irrational numbers. And here that doesn't mean that you can put q equal to 0 and that becomes irrational. Alright? Meaning if I'm saying any number which cannot be represented in the form of p upon q, so that doesn't mean that q can be equal to 0. Okay, the condition that denominator should not be equal to 0, that applies to both rational and irrational. Alright, so all the numbers which are written in surd form, okay, the surd form we will see later in this unit, but root 2, you must be well known with this number root 2, right? Root 3. I'm not saying root 4 because root 4 is exact and integer value natural number which is 2. Okay, similarly root 5 and so on. So all these numbers are irrational numbers, and if you will find out their decimal equivalent, you may find out their decimal equivalent, but you will see that there won't be any pattern after decimal point. And hence the property of irrational numbers is that their decimal equivalent is non-terminating and non-repeating. We had one category, as we have just seen in rational numbers, that we had one category of non-terminating but repeating digit. In irrational number we have non-terminating and non-repeating. Okay, so its equivalent is 1.414 and so on. I just remember till 3dp. Similarly for root 3 is 1.732, like this. So if you find out their decimal equivalent, there will be infinite number of digits after decimal point without any pattern. Okay, so I may write down this, that decimal equivalent will have infinite number of digits after the decimal without any pattern. Simply speaking, irrational number has a property of non-terminating and non-repeating. Okay. One more famous irrational number you will be surprised to know is pi. Okay. You will say that, sir, the pi value is, we say, 22 by 7, and this 22 by 7, as you can see, is in the form of p upon q, and q is also not equal to 0 in this case, so why not pi? is regarded as a rational number, not irrational. So the answer is that this 22 by 7 is the approximate value of pi. We say no, the approximate value is 3.14. Definitely that is the approximate value of 22 by 7. But again, that 3.14 is an approximate of the approximate value, which is 22 by 7. So 22 by 7 is not the exact value of the pi. Okay, exact value of pi is just pi. Since this pi is related to geometry in which is the ratio of circumference and diameter. So we are dealing with lengths, and lengths cannot be measured accurately. You get more precise instruments which can measure length more precisely, more minutely, but you cannot say that certain length is this much accurately. There is always a scope of improvement. Okay, so all these are the number systems, and lastly the number system is real numbers, which is the combined set of all these numbers. Okay, so if I represent this in pictorial form, that final set of numbers is real numbers. Real numbers is a set of all natural numbers, rational numbers, integers, irrational numbers, and so on. Right? So if I write down the pictorial representation of these number system, so the first number system came was natural numbers. So I put a small circle and write n. N stands for natural numbers. Then the next system came was whole numbers. If we add 0 to this natural number, the next number system becomes a whole number. Okay. Then came integers. Okay, so this set is integers. So this region, which is outside this yellow and red, this region basically consists of negative natural numbers. All those negative numbers are inside this ring. Okay, so this is integers. As you can see, integers, all natural numbers are whole numbers, all whole numbers are integers, but all integers are not natural or whole numbers. Next number system was of rational numbers. So again, a big circle. Rational numbers are denoted by capital Q. I haven't introduced you with the letters that we will see in sets. So rational numbers are Q, and lastly irrational numbers have gone somewhere. Okay, this is something which is outside these circles. So last number system, I will say that it is of real numbers denoted by capital R. Okay, so this is the pictorial representation of number systems that we have just studied. All right.